we'll do another recording. Okay, so we were briefly interrupted, I suppose. We had a brief difficult. Okay, there we are. Yeah, I was going to say hello, welcome to another week of statistics, and we're talking about tests of means, and we're going to go through the homework homework assignment, and we're going to look at inferential statistics. Someone asked a really good question, which has to do with some of the first stuff we're going to look at when we talk about inferences with means. And as I said before, for about I don't know, half hour or so, before we got disconnected, we basically can think about every facet of statistics in this latter half of the course. When we talk about inferential statistics, we're talking about making statements about beyond the data, but in principled ways. Inferential statistics is different than extrapolation. Extrapolation is pejorative. It means going beyond the data to make claims that aren't warranted. Statistical inference is making a principled statement with a probability, with clear, definitive, discrete statements about the probability of being of a type 1 error, which is basically of making a claim that is false. So stating a claim that is true, for example, when in fact it is false, that would be a type 1 error. And that happens if you have a claim in which that is consistent, that when you have, say, a hypothesized value, a point estimate and a 95% confidence interval that is consistent with your population parameter, but in reality the population parameter lies outside the 95% confidence interval, that would be a false alarm. It'd be a type 1 error. We also have a type 2 error, which is when you fail to reject the null when in fact the null is true. So that's a little bit less of a concern because we're often, but it's still a problem. It's basically making a claim that, well, this statement is not true because the population parameter lies outside of our 95% confidence interval or is inconsistent with our data. Those kinds of inconsistent claims are also problematic. But typically we're more worried about type 1 errors, and that's why we call them type 1 errors, which are because when you publish in science, you often want to make a statistically significant claim. You want to show something new. You want to make a statement about the world. So that's why it's actually called a type 1 error, because it was originally formulated as something of greater concern than a type 2 error, which again is a claim in which you think nothing doesn't exist, something does not exist, when in fact it is true. So it's basically a failure to make an empirical claim, as opposed to a claim that's what a type 2 error would be. It'd be sort of like, oh, I failed to show evidence of a statistically significant difference in means between two groups, or that my data are consistent with the population. I failed. Basically, that's kind of a way of thinking about it. Anyway, enough of that. We're going to go directly to the homework, and we're going to address an interesting question, which has to do with sampling size and the center of the sampling distribution. Those properties when we talk about sample sizes and that kind of stuff. If we run out of time, I'll post it online as a little tutorial. But I'm going to stop the video, in part because I don't want us to lose. I put it's internet connection anymore. It's been a little windy and rainy. That could be part of it too. Who knows? Okay, so I'm going to just scroll through here, and I talked about this cool data set, but I want us to get beyond these t-distribution models and this cool plot dist function, which is basically, if I do the question mark here, it basically shows us how to plot probability distributions. It's fun. And here we're talking about a t-distribution, but if I would put a question mark before it, oh, why doesn't that not work? Did I misspell it? Well, I think I probably need to load the Mosaic library. So it'll do a couple stuff here. And if we can remember, as you recall, you can also load your libraries here. And they're all clicked on. I'm going to click this one too. It's not the end of the world if it doesn't load. I believe plot dist is actually part of that. And yes, it is. The cool thing is you can plot all these kinds of distributions, probability distributions. Remember we talked about the normal distribution. And there it is. If we go to the help tab, going to, by the way, I just went right to examples. You can look at the R tutorials. I show you how to go sort of navigate or interpret the help file. I think it's very useful to go to examples first. I talk about other kinds of distributions. We're going to talk about chi-square distributions next week. Nope, sorry, the week after. We're going to talk about probability, a proportional test of difference. But most of the time we talk about normal distributions and some of its variants. This is it's a different kind, it's a type. But we also talk about t-distributions. I'm looking to see if they actually have one here listed. And do they not? No. Okay. That's okay. Well, let's take a look at the plot distribution of someone had asked the sample size of the center of the sampling distribution change shape of the, well, this has to do, okay, I think the question has to do with this property of a difference between a normal distribution and a, which is a, I'm going to retype this, right? It's basically a normal distribution. This is actually a standard normal distribution because it has a mu or mean of 0 and a standard deviation of 1. This is kind of the classic one. Standard means it's standardized. It's a way of interpreting and understanding, translating. It's kind of like a Rosetta Stone or a key between different kinds of metrics, numerical metrics. You can take, say, an SAT score, as we talked about in class. You can take an ACT score. These are different scores, but they have the same percentiles. You can score 90% better than everyone on the ACT or on the SAT, but the numbers are going to be different. So how do you compare those two? Well, you can translate them into the probability distribution, to their relative point in the probability distribution. Those are called z-scores, and that's basically what the standard normal distribution is. It's a way of talking and thinking about probability in a way that lets you standardize or compare different numeric metrics. So I know I said more. We're getting to that question about the difference between these two. Looks like we need to state our degrees of freedom here. That makes sense because the t-distribution is sensitive to a number of cases. So when we talk about the t-distribution, we can compare these. What happens when we increase the sample size? Well, it's an interesting thing happens. We're getting the shape of the distribution changes. And in fact, when you get a sample size from a t-distribution, for a sampling distribution, the t-distribution approximates or becomes more like the normal distribution. I know I'm repeating myself, I apologize. But the t-distribution becomes more like the normal distribution as the sample size increases. Those tails get fatter. It looks like it shrinks, but that's because the metrics are different. If you look at an N of 3, these are really fat tails. And by fat tails, I mean they're kind of how do I put it? Well, they're fatter on the corners. Sorry, that seemed to have opened up. If I can give you an example, I'll show you a picture, I think, of a t-distribution that I think is useful. And I think this answers a question. That question has to do with, well, what happens to your point estimate? Does your point estimate actually change, as the sample size increases? Well, technically, your point estimate doesn't change as your sample size increases, but your the width of the distribution will become will change, because if you have fatter tails and a smaller sample size, the t-distribution incorporates the lack of information you have when the sample size is 30 or less about. So when you have smaller sample sizes, you need to have a t-distribution. So even though your point estimate will be identical, your confidence interval will be too narrow if you assume the normal distribution. The t-distribution was basically invented and discovered to show that with a sample size of about 30 or less, you need to widen those confidence intervals and to reflect the greater uncertainty in your point estimates vis-a-vis the claim that you're making about the unobserved population parameter. So the question was, if a sample size increases, does the center of the sampling distribution remain the same? The sampling distribution is the same, but if you look at the t-distribution, how do I put it? The shape of the distribution changes. So here's a picture I have of that I hope clarifies this. It's a little blurry, I apologize, but this isn't from a book. This is actually from notes I have on hand. But it's a good summary of the t-distribution, and you can look at the comparison of the shapes. So if you look at this, you have essentially the standard normal is that purple here. I apologize, it's blurry. The t-distribution with 2 degrees of freedom is in light, is in that dotted red. So here we have that's what I call a fat tail. It's a little bit fatter, it's higher here. You're decreasing the probability here, and you're increasing the probability of a value of your point of the true of your point estimate falling here. And that means it widens your confidence intervals, because these are probability distributions. So the point estimate's not going to change. The center is still around 0, but the odds of your claim being true is going to be less precise when your sample size gets smaller. And in fact, if you look at the t-distribution with 9 degrees of freedom, it's a little bit larger. It gets closer to the normal distribution, but it is not. As it says here, t-distributions have more area in the tails than the standard normal distribution. Those other claims I think we've already covered. Basically, I think that this is the point I was making. The spread of the t-distribution is slightly greater than that of the standard normal. So there's more probability in the tails and less in the center. That's it, really. But it was good to compare those. Okay, I want to get to hypothesized testing. We talk about 1 sample and 2 sample tests of means, but these can also be one-sided or two-sided. And a one-sided test means that we're going to make a claim that we hypothesize that our mean or our average is less than a value or greater than a value. Those are one-sided tests, because basically what we're going to say is here's, given our probability distribution, we're going to assume that we're going to test whether or not our value is lower or lesser than that value. So that's a clear distinction we need to make between 2 sample tests and 1 sample test with a 1 or 2-sided hypothesis. So if you can see my little highlighter here we have the 2-sided hypothesis. So what this says here is 0 is the default, but this would be a test right here using this function. Let's assume that we're using our data set of the average number of hours of work per week. So let's do our FAB stats here of hours per week, and data we're going to use employed American Community Survey, and we're going to run that. And if we look at those numbers right here, right at the bottom, you can see that it ranges from 2 at the minimum. So there are people who are technically employed according to the Bureau of Labor Statistics who work 2 hours a week, and a maximum of 84. Again, this is within the sample. I can guarantee you there are people in the population who work more than 84 hours, believe it or not. But we're interested in our average. This is our estimate. This is going to be our point estimate of the number of hours that we observe in our 343 people randomly surveyed in the United States. We don't observe the number of hours worked on average per week in the population. That's the unknown parameter. There's only one parameter out there in reality. There is a reality out there. That's why we call it a parameter. And we call this a point estimate because we know that it is a single point in a probability distribution. We know it's a claim that is by definition measured with uncertainty. So we need to incorporate that uncertainty in our claim about whether or not we believe this data to be an empirically true claim, a verifiable or justifiable claim. So that's why we talk about point estimates and we talk about confidence intervals. So a one sample t-test here, which is two-sided, is simply the claim that where we state the null hypothesis here. So remember, we talk about what we're interested in. We talk about the null and alternative hypotheses. The null hypothesis here is going to be written something like this. It'll be, geez, it's hard for me to type it out and I can't write it out. But basically the null and alternative, let's see if I can open the lecture notes so I can show you what it looks like, because typing it out, I wish I had a chalkboard. It's not going to work. But basically the claim here is going to be that the difference, that the null hypothesis is that we'll say x bar is not equal to mu. You know what, I'm going to put this in English, okay? We're going to say our null hypothesis, which is going to be our estimated sample mean. We're going to say our sample mean does not equal the population mean. And I'm going to put hypothesized population mean. Okay, that's what that is. It says it does not equal. If you look at the equal sign with the X cross to there, that's our null hypothesis. Null hypothesis here. Our alternative hypothesis, if we reject the null hypothesis that they're not equal, then we're going to say, I'm sorry, look at this. Oh yeah, there we go. Equals. Our sample mean equals the hypothesized population mean. So it's a statement that 39 hours is statistically, probabilistically equal to the population mean. I don't necessarily like this because these kinds of claims are practical, but they are not necessarily probabilistic. These are null and alternative hypotheses, and we can support them probabilistically, but we can only make claims about those with uncertainty. Okay, so we have those. Let's hypothesize a population mean of mu here, two-sided. We're going to run that, and we have the output here. Here we have that thing called the t statistic. We have degrees of freedom, which is simply our sample size minus 1 because we had to estimate the average in the sample. We have our p-value, and one of the steps that I glossed over was specify your alpha before. We said a 5% probability of a type 1 error would be sufficient, which means that means 5% in 5% of tests like these, if we could have a sample, if we could have identical samples and tests such as this, we're going to make a claim about rejecting the null hypothesis when in fact the null is true. Well, looks like we reject the null hypothesis here because our p-value is less than 0.05. In fact, it's about 0.04. And I'm sorry, I got those reversed. Woo! this is the alternative. If you look at the output, I notice I got this wrong. The alternative hypothesis is that the true mean is not equal to 40. So and the 95% confidence interval is stated here, which shows that in 95% of samples such as these, our true population mean is not going to include 40 here. So technically that is our null hypothesis. Sorry, I got it mixed up. So this is the not equal sign. The null is the equal sign, right? So the null hypothesis is a statement about it's a statement about the consistency of our data with the population parameter, hypothesized population parameter. The alternative is when you reject the null. And we did. We reject the null and we show that our 95% confidence interval is 37 to 39. And the mean of X, this is our point estimate, it says sample estimates, but that's our point estimate, is again the mean that we found here. It's simply the mean. So what we have here is we have the observed mean. This is from the data. Then we have, based on the probability, on the sampling distribution, we have a 95% confidence interval, which is basically means that 95% of the area under their probability distribution, in 95%, sorry, it basically shows that our point estimate is with 95% of point estimates similar to ours. And if we did 20 tests, 19 of those would include an average number of hours worked that is less than 40. It's somewhere between 37 and 39. It does not include 40. 40 is close there. So because we're doing a two-sided hypothesis with a null, I didn't do a null of 0 because that would have been ridiculous. We formulated our statement. We talked about our null and our alternative hypotheses. We did an empirical test that uses an alpha of 5% and gives us a 95% confidence interval and permits us to basically make a statement about our null and alternative hypothesis. Here, our statement is that we reject the null hypothesis and to accept the alternative hypothesis, that our sample mean does not equal the hypothesized population mean. And if there are doubters out there, you show them the numbers, you tell them the data is the American Community Survey, they should know about it, if not. And this is basically how you do a one sample test for a mean. You have one sample, you have a claim about an unobserved population parameter, you make a statement about your null and alternative hypotheses, you look at and you have an alpha level that you specify. Typically, we're going to go with an alpha of 5%, which means a p-value of 0.05. I know that's some jargon there, but the main point is the alpha is simply how much leeway are you going to give? How much credence do you want? How much risk do you want to take about being wrong? The greater the alpha is, the greater you're increasing the probability that you're going to make a statement. You're going to reject the null when in fact the null is true. We don't really want to do that. So and convention typically will dictate a null, a hypothesized value of alpha of 5, which corresponds to a p-value of 0.05. And you want to find a p-value or probability value less than 0.05 if you are interested in rejecting the null hypothesis. Now this is two-sided because our null hypothesis and our alternative hypothesis are stated in terms of whether or not something is equal to something else. Now, there was with a null of there's a two-sided hypothesis with a null of 39. Let's do a one-sided hypothesis test. So we talked about the null. A one-sided one sample t-test that is a one-sided, one sample t-test. It simply means you're going to make a claim not about whether your mean is equal to the population or not, but you're going to test a claim about whether or not the value is less than or greater than about something, a particular value. So here we have, for some reason in the code, someone hypothesizes a value. Well, maybe not for some reason. There's always a reason for a hypothesis. Here we have a null hypothesis, which basically is very similar in wording. But it's going to be just basically, you're going to replace not equal. You're going to replace these phrases, equals and not equals, with greater than or less than. So this will be, I guess it'll be, I would say not less than. And then this should be does not equal. So, but notice what I did here. Everything's the same. All you're doing is you're expressing whether or not your mean is not less than something or less than something. That's a one-sided test because it means that you're not testing whether or not it's both less than or greater than something, which is whether to be equal to something else, right? For your value to be equal to something else, you have to reject both the idea that it is less than something and greater than something. One-sided simply means you're looking only at one portion of this probability distribution. What's the probability that it is less than this value? What's the probability it's greater than this value? That's all that this is. And the tests here are going to be the same. You're going to, if we have an alpha of 0.05, an 5% alpha, then we're going to basically look at our probability distribution here. And you see a 95% confidence interval. That's a little strange, and we'll talk about that. But the output is simply the same. We have a t statistic, which jointly with our sample size, which is our degrees of freedom, which is are the number of observations minus our estimated mean, that's going to give us our distribution, and it'll also give us our p-value. Our p-value is 1. That's basically impossible to have. It means there's a 0 chance of the null being true. So we're going to reject that null with great confidence. And the alternative hypothesis is that the true mean is less than 1. Did I say reject it? I meant, yeah. Wait, hold on for a second. Yeah, yeah, we're going to accept the alternative hypothesis that our sample mean is less than the hypothesized population mean. Because if we look at this, we actually know from our 2-sample test that our point estimate is 38.84, and that our distribution, our 95% confidence interval, shows it's probably around 37 to 39 hours per week. So basically, the idea that it is not going to be less than 10, the idea that it is less than 10 is sorry, I got this. I apologize. This is me not being able to write things. Our alternative here is our null hypothesis is what we're given, which is basically the default is, I apologize. Obviously 10 is less than, lies within our confidence interval. 10 is within our null. Another way to think of the null hypothesis is it's when our point estimates, our population parameter, or our hypothesized statement lies within our confidence interval. It means there's nothing new about the claim. The alternative is going to be that the claim that is made in the one sample test, that it is inconsistent. So I apologize because I just got the wording mixed up. Here, for one-sided test, when you talk about an inequality, the null is going to be whether or not it's less than or greater than the average is going to be less than or greater than the hypothesized population mean. So if you say that the population mean is 10, and our sample shows that it's 38, the null hypothesis states that our sample mean 38 is in fact so off that it grossly misstates the true population mean of 10. It's so bizarre to even think that the number of average hours worked per week would be 10. That's why we have such an absurdly high p-value. But that's what the null hypothesis is. It's a statement about whether or not our claim is actually less than our population mean in a one-sided hypothesis test, where your null statement is a statement about a population parameter being less than your sample mean. Your alternative is going to reject that. And that's what you see here, right? Because if you look at the wording here for a two-sided test, you have our sample mean equals the hypothesized population mean. The alternative is our sample does not equal the hypothesized population mean, right? So here we're in a one-sided test, we're saying our one-sided test sample mean is less than, or we could even say greater than, if we're going to do a different kind of the population mean, or we can say it's not less than. So in fact, we can think of all three statements, one-sided, two-sided, and three-sided tests, as statements about either equal to, less than, or greater than, or not equal to, not lesser than, or not greater than. I'm just rephrasing the null and alternative hypotheses so you can have them in one place, right? So when we made this statement that our null hypothesis, our sample mean was less than, the population mean is less than 10 hours, then we're doing a one-sided test, and we would claim that our sample mean is less than the hypothesized population mean of 10. And when we did the test, our alternative was our sample mean is not less than the hypothesized population mean. And we know that we rejected with our hypothesized mu or population a mean of 10, we rejected the null hypothesis that our sample mean of 38 was less than the hypothesized population mean of 10, and we accepted the alternative hypothesis that our sample mean is not less than the hypothesized population mean of 10. Okay. We can do one with greater. I'm going to change this. Let's change the value. I don't care what we're going to do. I'm getting bored of this. Let's do age here, if you don't mind. We'll stick with the same for pedagogical reasons. I apologize. I know we've gone over a little bit, but we lost some time. Let's do I don't know. We'll do 50. Oh, wow. And I'll do age, just so you can see that this works with regardless of the data. So here, what we're doing is we're basically we're making a statement about an average, and we're doing a one-sided test about whether or not our sample mean for age in the ACS is greater than 50. I'm going to do actually 40. We'll do 40 because it seems a little more plausible. Greater than 40. So that our null hypothesis is our sample mean, whatever it is is going to be greater than the hypothesized mu, or population mean, of 40. And if our p-value is less than 0.05, because we have an alpha of 5%, then we're going to reject the null hypothesis, and we're going to accept the alternative hypothesis that our average age in the sample is not greater than the hypothesized sample mean, or population mean. Sorry, I'm going to restate the alternative here. We're going to, if we have a p-value of less than 0.05, we're going to reject the null hypothesis and accept our alternative hypothesis that our sample mean is not greater than the hypothesized population mean. And of course, we're looking at age instead of hours per week, because I want to show to you the joy of discovery. So here we did a couple things. I always look at the p-value. This is expressed in scientific notation, so it means you're pushing that 0.7 decimal places to the left, so it's pretty close to 0. I always look at that first. Our alternative hypothesis, then, our null is rejected, and we can accept the alternative hypothesis that the true mean is actually greater than 40, but not by much. It is actually 44. That's why I sort of changed it around. It's actually a little bit older than I thought, but not too surprising. The mean worker in the United States, according to our point estimate, is 44. And our confidence interval for the one-sided test is basically one side of the curve. That's why it's one-sided. You're looking at the probability distribution from our point estimates to positive infinity. I didn't really explain that when we looked at the less than, when the other side of that probability, the confidence interval, but we're making a claim, when we're making a claim about an inequality, we don't have a 95% confidence interval that is bound by two values. We have it from our point estimate to, not a point estimate, we have it from our lower bound of our confidence interval to positive infinity, or we have it from negative infinity to the upper bound of our confidence interval. So here we see this would actually be the bottom of our 95% confidence interval, and then whatever else is greater, we don't care. Okay, so now we have that. That's kind of interesting. So I just showed you something that is probably interesting, I hope. You can run this code and you can see how this works, but I really want us just to illustrate three key points, which is basically slide 100 of the lecture notes show us how to do, show us I would say show us how to use the concepts we learn in earlier modules, you could say. In other words, basically how to test for means. I would just say that. It introduces and integrates all of those constructs, all those concepts that you use, like things like an alpha level test statistic, a null hypothesis, an alternative hypothesis, population parameter, a sample parameter, point estimate, 95% confidence interval. It includes all of those concepts in the 5 steps in the logic of research. And I think that's the most useful for you to learn the concepts. And what we did is we showed you how we talked about, and I apologize for the miswording here, but we talked about a one sample t-test, right? So this is when you have a mean in your sample and you want to test whether you basically want to test a claim about the population. So, and this claim is going to be in terms of less than, greater than, or equal to, right? And so a two-sided test is simply is basically a claim where the null hypothesis, null is where sample mean equals population mean. Alternative is not. And then we talk about the one-sided test, which is greater or lesser than population mean, and then the alternative is not. So we have a bunch of concepts here. We don't tend to talk about all of them, but we basically are showing that we're making a principled statement about the probability of our claim being true, as well as our probability of our claim being a false one. And that's what the alpha criterion level does. And that's what we do with statistics, essentially. Now, with inferential statistics, and that's what we're going to do from here on out. And I did talk about two sample t-tests, which we're going to focus on a little more, but just remember a two sample t-test is about the difference in two means. A one sample t-test is about one estimated sample mean. That's an important claim to make, and I made that distinction earlier on because two-sided and one-sided hypothesis tests are not the same as two-sided and two-sample and one-sample t-tests. Two samples are, we're going to talk about next week, but that's where the point estimate is a difference in two means. And you're going to see that more in experiments. A one-sample t-test, you're going to see less often in practice, but it's simply where you have one mean and then you make it, and that's what our point estimate is. And then you're going to test a claim about that. And I wanted to end on confidence intervals. We can change our confidence interval. We'll talk about the criterion of being 5 at the 5% level. You can have different alpha levels depending on your risk. There's a trade-off here. Basically, with a 95% confidence interval, which is what I'm going to do for age, you're going to see this most often in published research, although that is changing. This simply means that you have a p-value of 0.05 based on your criterion to make a claim about statistical significance. And if you have a p-value less than 0.05, you're going to reject the null hypothesis. And that gives you a confidence interval that is somewhat wide, but also has a relatively high probability of making a type 1 error, which is a claim that your statement, that you reject the null when in fact the null is true. Now, they don't like me making this thing here. There's a little error here. Did I do something wrong? They don't like me to specify that level. Let's just see what happens when I run the code. I think it's not necessary because the default is actually, yeah. The default is, it was complaining because the default, if you don't write anything, the default confidence interval will be a 95% confidence interval. So here we have this is for age. We have our point estimate of age. We have our lower bound confidence interval of 37, our upper level of 39. And that's our 95% confidence interval. Basically, if you have a different alpha level, that corresponds to a different p-value. It corresponds to a different, how do I put it? A different p-value. Sorry, different p-value, different alpha criterion leads to different p-value, which also changes your the width of your confidence interval. So an 80% confidence interval is 100 minus 8 is an alpha of 20. It means you have a 20% chance of a false alarm, making a false rejection of the null. But you're going to have a I'll show you. First, here we have that 95% confidence interval, and I promise you we're going to be done pretty soon. Here we have a confidence interval for age that's from 44 to 45. If we have a p-value, which is going to be an alpha of 20, basically you're going to have not that much lower, but you're going to have a tighter confidence interval. Wait. Sorry, I mixed them. The upper and the lower I got mixed up. Remember that the point estimate is in the middle, and then this is the bottom of the confidence interval. This is the top. So yeah, that is pretty tight. You basically have a very narrow confidence interval, which means that you have more of your probability space, probability distribution, that where your point estimate can fall outside of that confidence interval. 99% confidence interval means that you're being more cautious about claims you're going to make. This is actually, I think, more increasingly the trend in science. And that means that you only have a 1% chance, you have an alpha of 0.1. That means you have a 1% chance of type 1 error, of rejecting the null when the null is in fact true. But guess what? When you have a really low alpha level, you're increasing the beta, or I'm not sure if we really talk about this too much in lecture, but we increase the type 2 error. There is a trade-off between type 1 and type 2, because if you're so stringent about making empirical claims that you're going to make a wider confidence interval, which is what we're going to do. We're going to do this here. So here we have a wider confidence interval. They don't vary that much because age is pretty, I don't know, the data are pretty structured here. But basically, you have a wider confidence interval, the lower your alpha is. The higher your alpha is, the smaller your confidence interval. Also, the higher the alpha, the greater your chance of rejecting the null hypothesis and accepting the alternative hypothesis. The lower the alpha, the lower the chance of rejecting the null hypothesis and accepting the alpha. However, when you have a smaller alpha level, will in fact guard you against making false claims. It'll also increase your likelihood of failing to make an empirical claim when in fact you can. So there's no perfect solution here. As long as you're clear about stating what your alpha is, which is going to be about 5% typically, that's what we're going to say. But we tell you to make a claim about what the alpha level is, because when we know your alpha level, we know where you're coming from, and then we can make an assessment about the likelihood of the claim you're making or your conclusion. Because when I see an alpha, first of all, I would never let a journal publish anything with an alpha of 20%. I think that's ridiculous. And I think it's a way of gaming the system so you can get a significant result. The 20% odds of making a false claim is just way too high. And that confidence interval is just too low. It's just not conventional. It just doesn't work. But the reason statistics works and the reason I can make that claim is because you are communicating effectively your statement about the probability of chance and the willingness of the risk that you're willing to take about the claim you're making. And you're able to communicate that effectively. As I like to say, statistics is a principled statement of the probability or likelihood of your claim being true beyond the data. Okay, that's it. I hope this was helpful. I know I didn't go through the homework exercises, but I think I did something a little bit better, which was to guide us through one sample tests, which are one-sided and two-sided, and to review first the 5 steps through which you formulate a hypothesis and a claim, and you state those null and alternative hypotheses, and you make those clear for yourself and for others. As you can see, because I'm so used to doing 2 sample tests of differences, I actually inverted some of the statements, because as we'll see, the point estimate is about a difference of 2 means. But here, when we talk about a 1 sample test, we're just making a claim about whether or not our mean is consistent with some claim about the population. And that's all inference is. It's principled chance. So next time you hear someone criticize statistics and saying you can say anything with it, you can ask them, well, it's what can you do? How else are you not going to bring an umbrella tomorrow if there's an 80% chance of rain? Are you going to bring an umbrella or not? I would say If there's a 99% chance, I'll still bring an umbrella. And if I brought the umbrella and it was useless, that doesn't invalidate statistics. The inability of it to make an absolute claim about the future in political science, polling, for example, does not invalidate the beauty and the logic of inference. Thank you very much.